Welcome back to an academic warm-up for project or research in mathematics. This is part 2. In this we are going to have research framework for graphs from algebraic structures. Now in this video we are going to have what is meant by a graph from an algebraic structure, what are certain algebraic graphs, what are some of the fundamental combinatorial properties and graph invariants of an algebraic graph. Can algebraic properties be discussed via the properties of algebraic graph? Research framework and research pipeline. Now, first, algebraic graph is a graph G with vertices and edges. For that, first we need to have say A to be an algebraic structure, and here the vertices are nothing but the elements of A or substructures of A. And then edges is the algebraic relation which connect either the elements or the substructures of A. For example, we may have, say, in the case of group, if we consider A to be a group, which is an algebraic structure, if we take the elements of the group as vertices, so they are the elements of A, then they are the vertices. To connect them, we will impose the condition that two elements will have an edge between them, provided they commute with each other. So naturally, in that case, we have to have G to be a non-abelian group, because in the abelian group we know that already the elements will commute. So that means we will have always a complete graph. So there will not be anything much to discuss about that. So definitely we will be considering non-abelian group when we talk about commuting graph, which is one of the type of graphs that we can define on groups. So here we have a certain list of algebraic graphs: Cayley graph of a finite group, zero divisor graph of a commutative ring, prime graph of a ring, total graph of a ring, co-zero divisor graph of a ring, annihilator graph of a ring. So very few that we have mentioned here. Now, if we have ring, then what all that there have been graphs in that algebraic structure ring. So that list also we will see now, algebraic structure and graphs. So if we consider group, there are Cayley graphs, commuting graphs, power graphs, enhanced power graphs, non-commuting graphs, conjugacy graphs, subgroup graphs. In the case of ring, zero divisor graphs, unit graph, total graph, Jacobson graph, comaximal graph, annihilator graph, prime ideal graph. And in the case of field, Cayley graph, algebraic geometry graph, modules. As for modules are concerned, we have zero divisor graph of module and semi-group, Cayley graph of semi-group, and zero divisor graph. In the case of nearing, zero divisor graph of nearing. There are other graphs also that we can have on these algebraic structures, only very few that we have mentioned. And there are also papers on graphs on right ternary nearing. So in that case, ternary algebraic structure it is. Annihilator 3 uniform hypergraph, we can go to hypergraph. So because it is ternary, you can talk about 3 uniform hypergraphs. So annihilator 3 uniform hypergraphs, 0 annihilator 3 uniform hypergraphs. So fundamental combinatorial properties and graph invariants of an algebraic graph is what we are going to have now. Now, as for combinatorial properties of graphs are concerned, they are properties that describe the discrete structure of a graph, that is, how vertices, edges, and subgraphs relate through counting and arrangement. And correspondingly, graph invariants, they are nothing but the numbers or polynomials that describe a property of a graph and remain unchanged under graph isomorphism. So just to list them, we have this table: combinatorial properties and graph invariants. Connectedness, correspondingly you have vertex connectivity. For diameter, that is the maximum of the distance between any two vertices, so that is given by this graph invariant DIAM of G. And then cliques, clique number, coloring, chromatic number, domination, domination number, and length of the shortest cycle in a graph, that is girth, and number of edge crossings, we have crossing number. Now, can we have algebraic properties via the properties of a graph? So for that, we are going to have two examples. One is your commuting graph. So in this case, naturally, our uh, underlying algebraic structure is nothing but non-abelian group. So here, what is that non-abelian group? We haven't mentioned, but these are the some of the graph invariants that we can discuss, and what do they actually tell us. So that is for that only we are listing. We are having this slide. So commuting graphs, for that word is a group elements, non-abelian group elements, and edges pass those vertices which commute. And clique number indicates size of the largest abelian subgroup, and the connectivity indicates how close the group is to being abelian. And diameter 2 indicates the commutativity is almost global. That is, any two non-central elements, whether if they commute, then of course there you have the distance to be 1, or they both commute with a common element, something like this, is connected to B via C. So that is what the meaning of diameter being equal to 2. The meaning, what does it convey? That's our aim to discuss on this slide. So this doesn't mean that for all commuting graphs of non-abelian groups that you have this to be true. No. Just for an example that we are discussing. So pictorially we can have this graph as a translation device between algebra and combinatorics. So it is the translation device between algebra and combinatorics, and parameters are the vocabulary of that translation. These are the vocabularies. Right. So suppose I consider a non-abelian group, and the elements of them are the vertices for this graph, and the edges formed if and only if u and v commute, that is uv equals vu. So every algebraic object gets encoded as a vertex and edge. So and then you compute, after getting the graph, you compute the graph invariants, vertex connectivity, diameter of G, and clique number, chromatic number, domination number, girth, crossing number, and so on. So what the graph says in combinatorial language. So these are the combinatorial properties: connectedness, diameter, cliques, coloring, domination, length of the shortest cycle, number of edges, and so on. So see that these are the combinatorial properties. In turn, what do they tell us? We have just now we said it's only a pictorial representation of what we have said in the previous slide. So it tells us the largest set of mutually non-commuting elements, size of largest abelian subgroup, and how far centralizers are from intersecting. So centralizer of one element, n of A, is all those elements which commute with A. Algebraic, here also we are going to have n of A, that in the graph context that denotes the neighborhood of A. In the structure context, that is algebraic structure context, n of A is normalizer or centralizer of an element A, those elements which commute with A. So that is what here they mean. So this is as for commuting graphs are concerned. Next we are going to have for zero divisor graph. The zero divisors, particularly we are going to have there are various algebraic structures, that is rings, for which you can talk about the zero divisors, but what we have considered here is Zn, and that too in when we have n to be 12, what happens. So that is what is given in the slide. We calculate the zero divisors of Z12. They happen to be 2, 3, 4, 6, 8, 9, and 10. So we form, see, actually the table for Z12 has 12 by 12. Each on 144 cells that you have, but here we have got only 7 elements as the zero divisors. So now to get the zero divisor graph of Z12, zero divisor graph, of Z12, we need to list out the 0 divisors. They are the vertices of this graph, and which element has an edge with other element. So that can be seen from the table. So here 2 and 6, the product gives you 0. 0 divisor none, both of them are non-zero, but yet the product gives us 0. So you have the corresponding set consisting of this element, singleton 6 we have, and annihilator of this element by the definition of annihilator is 6, and annihilator is a substructure, so 0 must be included. So with what we have, just we have mentioned, so each one should have 0 as structure, substructure of Z12. So in the same way here, as for 3 is concerned, with 4 it gives me 0 because 3 multiplication modulo 12, 4 is 12 mod 12, which is 0. And here 3 times 8, so 24 mod 12 gives us 0. So you will have an edge from 3 to 4 and 3 to 8. From 3 to 4 and 3 to 8 also. So like that, for each and every element from the table, we can draw the 0 divisor graph, right? Now, more than that, see, our aim is to know whether from the graph any algebraic property can be seen or not. So that is what is mentioned here. Given any 0 divisor graph, the graph hints at ideal structure. That is, the neighborhood containment order is the ideal inclusion order inverted. It is something like this. Here n of 2 stands for neighborhood of 2. So neighborhood of 2 contained in neighborhood of 4 would imply that the ideal generated by 4 is contained in the ideal generated by 2. So that is what this statement means. And how we compute all this, that we will see one by one. Here to compute the neighborhood of A, any node or vertex that you can consider. So locate a node A in the graph. It can be anything from the graph that you have this, and collect all vertices directly connected to A by an edge. Call that collection as n of A, neighborhood of A. So here, for example, if we consider 4. So what are the elements which could be present in n of 4? So it will be 3, 6 and 9. And so your n of 4 is that, and when you compute annihilator of A, you will have to include 0 in that. Right? So we have annihilator of A to be n of A union singleton 0. So here all these should have 0 to be included in the collection. So locate a node A, collect all vertices directly connected to A and denote it as n of A. Annihilator of A is n of A union singleton 0. You should include 0. It is because that annihilator is a substructure. So it should be there in that annihilator of A. Now annihilator of 4, according to this, already we said that 3, 6, 9 are in n of 4. So you must have annihilator of 4 to be there. Similarly, annihilator of 8. When we consider 8, again 3, 6, 9, along with that 0. So n of 4 is this, n of 8 is also this, and in this case you have. So here we have mentioned one more thing. This implies that ideal generated by 4 equals ideal generated by 8. So that directly we cannot have. For that we have to have the algebraic proof for them. So that is what we are going to have in the following slides. So that once that is known, all this that we are going to establish with A and B, that we are going to establish, so that here you can say that from the graph the ideal how they are arranged, so that can be easily seen. So that is the as for whether we need to do algebraic graph, because already algebraic properties that we know from the computation, but do we actually need it? So for that the answer is yes. And for that, the proof we are going to have in the following slides. We are going to actually show that annihilator of A is nothing but the ideal generated by n by d, where d is nothing but GCD of E and n. Suppose I consider annihilator of 4, you find the GCD of 4 and 12. This is, in this case, is 4. So 12 divided by 4 is 3. So annihilator of 4 is the ideal generated by 3, which is the set which consists of 0, 3, 6 and 9. Because the next one, multiple of 3, 12, again gives back you that 0, because we are in Z modulo 12. So we have, so that is the meaning. We are going to have the proof for all this. But the meaning, what does it convey? That how do you relate annihilator with the ideal generated by which element? So now we'll see the proof. Before we actually go to the proof, um, what we can say about the graph? It's a lossy compression of the table for Z12. Is of the table now, what is we have mentioned here in the previous slide, that is not the table that is given here. It is the table for this multiplication table for Z12. So that we have 11 element, because 0 we usually exclude when we consider the multiplication table. So excluding that means 11 by 11. So when you compare that with this, you may say yes, some information is lost. So we have, in that case, you say it as lossy compression, and as it throws away all the non-zero products and keeps only the zeros. That loss is actually a gain. Reason is, for ideal theory and annihilator structure, the non-zero products are always noise, because from that non-zero products we are not going to infer anything, so they become noise. So for that, this lossy compression what we mentioned will actually be a gain for us. So that is the meaning of the statement. And here the procedure, we list n of a neighborhood of every vertex v. If n of a equals n of b, what does it say? A and b are in the same ideal. This is from the graph that you see, and this is the algebraic inference. And if n of a is contained in n of b, means the ideal generated by b is contained in ideal generated by a. A larger annihilator is smaller ideal. That gives larger annihilator, because once I know my n of b union singleton 0 gives me the annihilator of b. So large annihilator, when this is large, that will result in a smaller ideal. So the same thing is only given here also. The vertex with the largest neighborhood, same thing, instead of annihilator with the neighborhood it is given. The vertex with the largest neighborhood is the element of the smallest ideal. The vertex with the smallest neighborhood is the element of the largest ideal among zero divisors. Right. So in Zn, we wish to establish, that is what we mentioned, in the previous slide, n of a contained n of b should imply ideal b. Ideal generated by b is contained in ideal generated by a. So this is the main result that we need, for which these results are to be established. The first result is the ideal generated by A is same as the ideal generated by GCD of A and N. And we will be, this is very obvious, N of A, the neighborhood of A is all those zero divisors, okay, whose product with A should be 0. And by the definition of annihilator of A, it is all those elements which are annihilated by A. So from the definition itself, n of A means annihilator of A. Next, to prove this is result 1, this is result 2. Annihilator of A is contained in annihilator of B means ideal generated by B is contained in ideal generated by A in Zn. Right. Now, congruence classes modulo n, the collection Zn means. So now first result, ideal generated by A is same as ideal generated by GCD of A and N. Now for convenience sake, let us denote GCD of A and N to be D. Then D divides A, D divides N. That is the definition of GCD. D divides A, D divides N. So because D divides A, you can find an integer A prime such that A is equal to A prime D, or which is same as dA prime. And the same way, D divides N, so N is equal to some integer times D, that integer is taken as N prime. So for some integers A prime and N prime with the GCD being 1. Why that GCD of A prime and N prime should be 1? Now suppose, so this is separate track, right? Because this is needed in proving the main result. So we will give the proof for this also. Now suppose C is GCD of A prime and N prime, then C divides A prime and C divides N prime. Now C divides A prime means A prime is some integer times C. Now this implies A is a DMC, the product of D, M and C, because A is equal to DA prime. A is equal to DA prime. So you have your here A is equal to DA prime and your A prime is MC. A is equal to DA prime, and in that A prime is replaced by MC. So you have A to be DMC. This in turn implies this is integer times DC, which means DC or CD divides A. So that is the interpretation from here that we are going to have. And similarly, N is equal to Dn prime and C divides N prime. So you have CD dividing N. The same explanation. So CD becomes a common divisor of A and N. CD becomes common divisor of A and N. But already what we have said, D is the GCD of A and N. So if C happens to be greater than 1, see the value that C can take is either 1 or greater than 1. Our claim is it is 1. Suppose it is greater than 1 means you multiply both sides by D. That's possible because D is positive GCD. So you have CD to be greater than D, which contradicts the fact that D is the GCD. You cannot have any number, any other number which divides both A and N and greater than D, because D is the GCD. So this tells us that C can only be 1. If C is 1, then you conclude that GCD of A prime and N prime is 1. Right, we need it, that's why the proof is discussed. Now coming to this part, our job is to show that ideal generated by A is equal to ideal generated by D, because GCD of A and N is taken as D. Right, now for that we'll prove that ideal generated by A is contained in ideal generated by D and vice versa, D contained in A. That is ideal generated by D contained in ideal generated by A. Right, now you take your X and X in A, and that is the ideal generated by A, which means X is some multiple of A, take it as that integer as MC. So X is equal to MA. Now A is replaced by DA prime. So this is what we have. So it is some multiple of D. So where will this X be? It will be in the ideal generated by D, because your X is written as some integer times M integer, A prime integer. So M integer times D means D must divide X. So you have or another one multiple of D. So it should be there in the ideal generated by D. So X in A implies X in the ideal generated by D. Therefore ideal generated by A is contained in ideal generated by D. Now you consider for the reverse part Y in the ideal generated by D. Now we have said already that GCD of A prime and N prime is 1, which means we can find integers X and Y such that A prime X plus N prime Y equals 1. We will multiply throughout by D, so we get this, and this dA prime is nothing but A and dN prime is nothing but N, so we have this. So in this we are multiplying both sides by D, you get this step, and using this you get this step. D is equal to AX plus NY. So this implies now this is modulo n. Yeah, everything is taking place in Zn. So modulo n means this part will not be there. So and what remains is d equals ax. It's a multiple of a, which means it should be there. Which should be there. D should be there in the ideal generated by a. Right. So here you have your yeah, D being element of ideal generated by A, you naturally have your this one, that is even though we started with y in D, even though we started with y in D, even D is also there in the ideal generated by D. So we have made use of that here. So D belongs to ideal generated by A. D is already there in ideal generated by D. So you have ideal generated by D contained in ideal generated by A. So from these two we have ideal generated by A to be equal to ideal generated by D, which is nothing but GCD of A and N. Now we have to have the second result also, in which we have to prove that annihilator of A contained in annihilator of B means ideal generated by B is contained in ideal generated by A. Now in Zn, let us consider GCD of A and N to be say D and GCD of B and N to be E. Then annihilator of A is nothing but the ideal generated by n by d, that is all multiples of n by d mod n. Why is it so? So for that we have the proof here. Annihilator is all those elements of Zn which are annihilated by A. So the meaning is mathematically this is how we express it. Now you have when you consider an element, this is the set. Okay, so if and only if when we put, then equality will come automatically, right? So when you consider an element in annihilator of A, this implies that Ax is congruent to 0 mod n, which means by the definition of congruence modulo n divides Ax. So this in turn implies that n by d divides A by d x. But n by d and A by d are relatively prime. N by d and A by d are relatively prime. Why is it so? When you have A and N, GCD of A and N, you have taken to be D. So GCD of A by D and N by D must be relatively prime. So because these two are relatively prime, we are borrowing a result from integers that A divides BC, in which A and B are relatively prime means A must divide C. A must divide C. So it is that we are using here. So n by d must divide x. Or in other words, x is a multiple of n by d, or x belongs to the ideal generated by n by d. So xn, actually x belonging to annihilator of A, it should have been x belonging to annihilator of A implies and implied by. So all these steps can be reversed. So you have equality here. This is a structure, this is also a structure. So annihilator of A is n by d and annihilator of B is n by E. E is GCD of B and N. Now annihilator of A contained in annihilator of B is my assumption say. Then every multiple of n by d, every multiple of n by d is a multiple of n by E. So that n by E divides every multiple of n by d is a multiple of n by E. So we can say that n by E divides n by d. And cancelling that n, what we conclude from here is d divides E. When d divides E, we have ideal generated by E to be contained in the ideal generated by D. Because when you have d dividing E means E can be written as some integer times D. So E is in the ideal generated by E, and E is a multiple of this. So we have E belonging to D also. So you have ideal generated by E contained in ideal generated by D, but E is nothing but GCD of B, and this one D is nothing but GCD of A and N. So GCD of Bn and GCD of An, we have the relation. But this is nothing but the ideal generated by B, because of the first result, which states that ideal generated by A is nothing but GCD of A and N. So we have from that ideal generated by B contained in ideal generated by A. So this is when you have annihilator of A contained in annihilator of B, implying this, right? Now we'll go to N of A. We'll go to N of A, neighborhood of A, which is contained in a neighborhood of B. So a neighborhood means it is those elements which are connected to A. What is the connection? Those two must be zero divisors. The product should give you 0. So you have this to be all those elements in this such that AX is 0. But that is contained in all those 0 divisors such that BX equals 0. So this implies, this is the meaning of N of A is this, and meaning of N of B is that. So from this we have annihilator of A to be contained in annihilator of B by the definition of annihilator. It's only interpretation. This is implication, this is interpretation. So this is what we have. But annihilator of A contained in annihilator of B implies annihilator of B contained in annihilator of A. So we have established what is required. What is required? We have to have N of A contained in N of B implies and implied by the ideal generated by B contained in ideal generated by E. So it is this concept that is used here to conclude the ideal generated by 4 is contained in ideal generated by 2. So inclusion is reversed. That's what is mentioned here, and that is seen also. So we have this result also we have established. So we had so far one from zero divisor graph, the other one from commuting graph, how the graphs tell us the algebraic properties of the underlying algebraic structure. Right. We can also talk about, once I have zero divisor graph, this is for the Z10, we can talk about the line graph. Now why should we study about the line graph? Because line graph promotes the hidden edge world of this into a visible vertex field. What becomes edge over there will become an ideal. That becomes a vertex in the line graph. So the line graph L of gamma of R of a zero divisor graph gamma of R is defined as a graph with vertex set to be as edges in gamma of R, zero divisor graph. That is, the vertices of line graph L of gamma of R represents an edge of gamma of R, and distinct vertices in L of gamma of R are connected if and only if their corresponding edges in gamma of R share a common vertex. So this is the zero divisor graph of Z10. So you have 5 with 2, 5 with 4, 5 with 6 and 5 with 10. Correspondingly, when you draw the line graph of the same one, it will be like this. So those edges which share a common vertex, you have one to be 2, 5 and the other one 4, 5, 8, 5 and 6, 5. So this is how you have the line graph of zero divisor graph. Now a few more list of algebraic graphs. Zero divisor graph, non-zero zero divisors of R are the vertices. X and Y are adjacent if and only if xy equals 0. So mainly, these are introduced by Anderson and Livingston. And total graph ring, if you consider ring, two distinct vertices x and y are adjacent if x plus y is a zero divisor. and x related, I mean this is for the next one. So you x plus y, two elements are adjacent if the sum is a zero divisor. Sum is a zero divisor. Is it of R means sum is a zero divisor. So it is introduced by Anderson and Badawi. And prime graph, x related to y should be 0 or y related to x should be 0. So that was introduced by Dr. Satyanarayana. And co-zero divisor graph, that is you have in that two distinct vertices A and B in R are adjacent if and only if A is not in the ideal generated by B and B is not in the ideal generated by A. Along with that, the order of x no, this is for the next one. So this is what you must impose. The condition to be imposed: A doesn't belong to BR and B does not belong to AR. So that is introduced by Alchemy. And next one is co-prime graph of graph, in which the orders of x and y are related provided their orders are the GCD is 1. Okay, so you have, of course, G means we are considering group, and X, my, etal, they are the um, one who found or who have discussed about this. And co-maximal graph of a ring R, A and B are adjacent if and only if RA, the ideal generated by A plus ideal generated by B equals R. And zero annihilator graph near rings not a right ternary. Non-zero non-unit elements in R, you must have annihilator of x intersection annihilator of y to be singleton 0. So this is when you want to have an edge between them, then this is how you can define the algebraic relation. Zero annihilator graph, non-zero non-unit elements in R, annihilator of x intersection annihilator of y should be 0, singleton 0. And then the order graph, order of h divides order of k means, then you have we have, this is the condition, and the elements taken are the vertices are nothing but subgroups of G. And nilpotent graph, nilpotent elements, then we need to check I mean it is AB equal to 0 even for nilpotent elements that you have. Their general 0 devices we had here, nilpotent elements. So these are the authors, and not for all that we have mentioned the authors. So it goes on and on. Now this is your research pipeline. You have the starting point. So these are the actually research framework. You consider all these are to be dealt. One second. Line graph. So these are the framework in the sense that you need to have the starting point, namely the algebraic structure, and then the how. So once you have algebraic structure, what should be the vertices and how you join the vertices by an edge, the condition. So condition is the second one. After getting the graph, you're finding the parameters, and then just check from them, you're able to conclude any of the algebraic properties. So the research pipeline goes like this. Start with here, even though we have said it as a ring, or you can even have groups and so on. So algebraic structure we need. Then we have to select elements, define adjacency rule, then construct the graph, and then graph parameters are to be determined. When you do more and more examples, in the sense even Zn itself you take. So when you take that Zn, for various values of n, because n can be just a prime number or just a product of two prime numbers or product of three prime numbers or p square q form or p square q r cube, something like that. So for various values of n, when we construct the graph, we will discover some pattern. Then with the help of the pattern, try to prove theorems and then generalize to other algebraic structures. So here ring, when you consider, usually Zn or polynomial rings or matrix rings or finite commutative rings, product rings, that is direct product. So usually they are considered as algebraic structures, and then selecting elements. It can be zero divisors or substructures, ideals, units, elements, idempotents, elements, nilpotent elements only. And then define adjacency rule. Vertices are elements, substructures, elements are substructures, and edges are nothing but the algebraic relation. When you consider, you may have zero divisor graph or unit graph or ideal graph or commuting graph or nilpotent graph and so on. Then for that particular graph, compute the parameters, namely connectivity, diameter, Clique's chromatic number, and domination. Discover the patterns, detect patterns after computing many examples. And once pattern are seen, extend results if possible to near rings, semi rings, and modules. Okay, so you have these are the important points that we wanted to have in this video. So research framework is for the particular one particular graph that you consider. No, so it becomes a part of research framework, is part of the research pipeline. So your starting point is, you have to do all this. Then it's not that the parameter that what I mean, it's not the algebraic relation so far people have considered. You can find out, you can even define your own, that this is unnoticed so far, nil clean ring and all, later only they have developed, not at the beginning itself. So somewhere they would have defined, so that you have to search, and that must be the algebraic relation in your paper. And then the rest, if you want to compute, you see whatever result you want to see at once, you need to definitely start with Zn. That doesn't mean that only with Zn the entire algebraic graph lies. No. It can be for polynomial rings, matrix rings, finite commutative rings, product rings, and so on. So do not think that it's only for, because whatever paper that you may see may be mainly with Zn, congruence modulo n. So that doesn't mean that the entire algebraic graph is defined only for that. So keeping that in your mind, when you proceed, you will get nice results. And actually, as for graph is concerned, you have predefined subclasses are already existing. So for that, the properties are checked. Okay, you are defining an edge. So there, even graph labeling and all, various types of labeling that you are defining, and then you are checking it for the standard graphs. Here, graph is not known, and you cannot say that for n equal to 12, you see one type of graph means the same thing for n equal to 13. No. So you don't have, like there you had family, like that you don't have. So each one will be of one type. So definitely it will be an interesting one. So research in, as for algebraic graphs are concerned, it will be it will be an interesting one, and lot insight that you can have. Okay. very good insight that you can even have as for algebraic structure itself is concerned, which that you would not have noticed. All that you will notice when you once you draw a graph and see the properties. So again, one more happy journey with your research as for algebraic graphs are concerned. Thank you.